Welcome back to Kinetics, Gen Chem 2. How's my favorite Gen Chem 2 class doing? We are going to continue our Unit 2. This is our second video. We are still in kinetics. We're just going to get a little bit deeper and do a little bit more problem solving. So the focus of this particular video is going to be our rate law. This is going to get a little bit deeper into our kinetics and our rates, and also just a little bit better with our data and what questions we're asking and what questions we're answering. So let's do a little bit of a recap. Where are we already? And then let's tie to that our rate law. We're going to add to it. So our previous video and what we've already looked at has been our general rate expression. Okay, now this is the most general. And we're going to keep evaluating our data. So this is actually really the least informative in our data. But it's a really good place to start. We're always going to start there and keep in mind what we're actually looking at and what we're studying. And for our kinetics, we're going to literally take reactions and time them. We're going to want to see, okay, how long does this reaction take? And we looked at some general data on our last video for this. For our general rate expression, we looked at several points of data. So one of the things we have to do is if we're just looking at really 2 points of judging that reaction, we really are not gaining a whole lot of information. It's a good place to start, but it's definitely not the end-all be-all. And what do I mean by that? Well, let's think about it. Let's take a general picture of a reaction. If our reaction is changing our concentration over time, and we learned that one of our factors in changing or affecting rate is concentration, we have a big question here. So as our concentration is changing, so is our rate. So we saw in our last video that typically what we need to do for general rate questions is as soon as we just take two different times, let's say we take 0 seconds and 10 seconds, and we judge that concentration. Okay, that's actually only going to give us a picture of that rate between 0 and 10 seconds and that gives us an average rate. And then if you think about it, as soon as we hit this 10-second mark, didn't this just change? So now if we go another 10 seconds, well, wouldn't this rate be even different than your average rate? Because your concentration just went down, your rate is going to go down. So what we saw in our last videos, it's actually quite typical to generate several points of data and actually plot them. And what we would notice is that typically that is not linear, because as we lower that concentration, our rate starts to slow down. So we'll do quite a bit of graphing and quite a bit of data and crunching in our kinetics unit. We did learn something pretty specific in this last video though, and that was that at any given point, we had an instantaneous rate. If we compared two of them, we had an average rate. And if we plotted them, we got something pretty special, and that our slope could actually give us our rate. So it is pretty beneficial to plot those, to generate as much data as you can, and then plot those. And this is where we're heading in our next sequence of videos. How do we get the most information out of our kinetics data? So I like to always start in the same way. You have to have a picture of your reaction. Your general rate expression is how we're going to actually picture and study what's happening in our reaction. So we've got to get good at writing that, and let's start there. I would put this on a cheat sheet somewhere. This isn't going to change. If you've got any chemical reaction and you have reactants forming products, then your general rate expression will be equal in each way to your rate, and you will have a general change in concentration over a change in time. And we ended our last video with including moles. So we've got good at writing our general rate expression. Now we're going to add to it. So we did learn that, wait a second, our rate is going to change as our concentration changes. That's awesome. Thank you, Mother Nature, for making that just a little bit trickier. But here's where kinetics starts to get really fun and teach us a lot. If our rate is changing with our concentration, okay, that's awesome if we see how that could happen, but let's take a step back and let's try and figure out, how does your rate change as your concentration is changing? And this how is going to give us our next piece to the puzzle. This is what is going to lead toward our mechanism. So how do you actually study how your rate changes as your concentration changes? And then as we get that information, what does it really tell us? It's going to end up telling us something called our reaction order, or the order of our reaction. And let me show you what our rate law actually looks like then. We're going to take a general rate law, and I'm going to add it up here to our general rate expression. And our rate law is going to tell us, I'm going to add it right here because it is the same rate for that reaction. Our rate law is going to tell us how. So our rate law has typically a rate constant, that is a little k. We will use that in a couple of places this semester. We are going to have a rate constant. That rate constant will be specific to each reaction. So I can't give you a number. We're going to have to solve for it. That is a constant for that reaction. And then we have understood that all of our products and reactants are completely connected. So as our products or our reactants disappear, our products appear. So in a rate law, we want to look at what happens when our reactants start to disappear, because then our products have to appear. That's how that happens. So our rate law actually only includes reactants. We're going to study how they disappear. So I'm going to take each reactant. In this case, we'll put A and B in there as our reactants. And then here's where the how comes in. This is what Mother Nature has to tell us. This is how we figure that out. We are going to have an exponent here, general exponent. Now this is probably one of the hardest parts of kinetics, is that this exponent will give us the order of our reaction. Aha, there is our reaction order, but it is not moles. We have to solve for it. So let me put that in caps. That is not moles. It may end up looking like moles, but that is not just as simple as taking, notice this is not little a and little b. This is literally two different exponents. This is something that we are going to have to solve for. The only way to get order is to actually solve for this. You need data. Order comes from Mother Nature, not any way that we can predict that. So let's put that in a nice highlight here. Okay. All right, so let's back up a step. So for any reaction, what is the rate law? The rate law is a rate constant times each of your reactants, and they are to an exponent that we have to solve for. So when we consider our rate law, we're going to solve for rate constant and exponents. So let's take an example. Let's put all this together. We need an example. Let's take a reaction. I took this actually from the Brown-Lemay textbook. So that was an older version of the Brown-Lemay textbook because it's nice to have actual data for these. So let's take a reaction like this. And let's write the general rate expression. And then let's write the rate law. And they are actually connected. So as we are going down, and then, well, let's double check. Are we balanced? Hang on. Looks like we need a 2 there. Okay. So as we're writing this out, our general rate expression is going to be that ammonium ion. It is going to change over time. And we have just 1 mole. It's going to disappear. That NO2 is going to disappear over time. Our N2 is going to appear over time. And our water is going to appear over time. And then how do we put our moles in there? Right there, okay? Now that will be equal to a rate. Now this is beautiful. The general rate expression correlates concentration and time. But now how the rate changes with concentration is your rate law. So then let's go ahead and add right down here that same rate is equal to our rate law. So, okay, what is our rate law? Well, every rate needs a rate constant. And then let's take our reactants. Okay. So all of these are equal. And our rate law, you'll notice what we're looking at is how our rate changes with concentration. So what should our data look like? Our data should be concentrations of initials and your rate. And your rate is changing. And look at these rates, they are changing. So now we want to study exactly how that rate changes. How does that rate change as you change concentration? And then when we figure that out at the end, it's like a cliffhanger, then we'll use reaction order in our last video to say, okay, well, if your reaction order is first order, it behaves like this. If it's second order, it behaves like this. So this is our first step towards our mechanism. So in this video, let's learn how to actually solve for our rate law. Okay, it's actually pretty fun. You have to take data in order to do this. This does not just come from me making up numbers, thank God, because I would screw that up. This is why I took it from a textbook. We have to take actual data to do this. So how do you solve for anything? If we have our general rate law, and then we've written it out, now we choose wisely, is what I'm going to call it. So step number 1, we wrote our rate law. Okay, so we have some idea of what we're looking at. Now our number 2, I'm going to call it, oop, my pen got a little fluffy there. I'm going to call number 2, choose wisely. We are going to compare 2 experiments, and what we're looking for is in one of these experiments, we would love it if the concentration changes. Done. Look at that, number 1 and number 2. But then look at the other concentration stays the same. And then look, our rate changes. So what we're doing is saying, okay, hang on a second. In these two experiments, only one thing changed, only one concentration, and then look at the effect it had on the rate. So how do we solve for that? We're literally going to compare the two of them. So maybe take a screenshot real quick because we're going to use that data. I'll probably have to scroll just a little bit. We are going to compare that second experiment, that rate number 2, this one. And we are going to compare it to that first rate because we saw a change in our rate and a change in our concentration. So I like to set it up like this. I typically choose the higher rate to be on the top. Just makes your math easier. And then our our rate law is going to be a rate constant times that ammonium. Okay, well, we actually have a concentration for that ammonium. And in our second experiment, let's go up and look at that. So experiment number 2, let's go ahead and highlight 0.02 molar. Let's write that in. Okay, and then let's compare that to 0.2 molar for the NO2. Now both of these have exponents that we're solving for. And then now let's compare that same thing, but this time for the first experiment. So 0.01 concentration. Let's look at that second one is 0.2 molar. Okay, the reason we choose wisely is, holy crap, check it out. Look what I get to cancel here. And let's go ahead and give me 1 second. Let's actually add the rates. What was rate number 2? Rate number 2 is 10.8. Wow, I just hit something and my screen just freaked out on me there. Whoa, it just froze everything. Okay, for some reason my screen is frozen. I may have to stop and start again.